Hi, everyone. Thank you for joining us for today's webinar. My name is Sakshi Sethi, and I manage OIDA membership here at OSA. I'm really excited to introduce today's presentation. It's by VPIphotonics. I'd like to go ahead and introduce today's speakers. We have Dr. Jim Farina, who's U.S. Managing Director and Director of Technical Services at VPIphotonics. Eugene Sokolov, the Senior Photonics Application Engineer, also from VPIphotonics, and our moderator, Chris Maloney, Director of Business Development from VPIphotonics. So with that, I'd like to thank you guys so much for attending. I'm going to go ahead and kick it off to Chris to get us started.
Thank you, Sakshi, and thank you everybody for joining us today. As Sakshi mentioned, we're from Photonics, and the talk today is titled Migrating a Photonic Integrated Circuit Simulation to a System Design. And specifically, we'll be talking about a Silicon Micro-Ring Modulator implemented in a PAM4 link. Before we begin, I'd like to just give a little bit of background about VPIphotonics and who we are. We've been around for over 20 years, and we have operations out of Berlin, Boston, and Minsk. And today, Jim and Eugene are joining us out of the Boston office. We provide professional simulation software for end-to-end photonic design automation, anywhere from waveguides and fibers up to integrated photonics to fiber-based lasers, optical transmission systems, all the way up to the network for link engineering and equipment configuration. We also provide technology consulting. Most specifically, we participate in European research projects. One in particular is the Unicorn project, where we are helping with quantum key distribution development. And here's a glimpse into our product portfolio so that you understand the landscape that Eugene and Jim will be talking about today. We provide software tools for different levels of abstraction. Starting at the bottom with device simulation, we have a mode designer tool, but then we also move up into component design. We have this VPIcomponentMaker tools for fiber optics and photonic circuits. And as a toolkit add-on for photonic circuits, we also support various PDKs at different foundries. At the transmission design level, we have our VPITransmissionMaker tools for optical systems. And this tool also has some toolkit add-ons for digital signal processing, DSP library, as well as quantum key distribution. And these two tools, the optical systems tool and the photonic circuits tool, this is where we will be highlighting our examples in today. So Eugene will be talking about photonic circuits, and Jim will bring things up to optical systems, both in the same GUI. And at the very top, we also have some parametric link engineering tools for network design and equipment configuration in our link designer and link configurator. To give you a brief outline of today's talk, Eugene will get us started going through a photonic circuits example, highlighting a Silicon Micro-Ring Modulator. And we chose that type of device due to the attention that it's been getting for its small footprint, low power consumption, and high operating speed. And then Jim will join us and discuss some of the challenges of simulating both a circuit and system level together, and take us through an optical systems example, specifically a PAM4 transmission system based on the micro-ring modulator. And we chose the PAM4 transmission system because it's fairly widely used inside and outside of the data center to connect racks, to connect buildings, as well as connecting regional sites. So with that, I'll just mention that please submit questions to the Q&A box. I'll keep an eye on those during the talk. and we'll ask Eugene and Jim those questions at the very end. So with that, I'd like to turn things over to Eugene.
So hello, everybody. Thank you, Chris and Sakshi, for the introduction. So I'll start sharing my screen now. Okay, just to be sure if you can see it and if you can see my presentation now. So as Chris mentioned, I'm going to talk about integrated photonic circuits and specifically about how Silicon Micro-Ring Modulator could be simulated. And to start with, let me show you first the simplified system configuration we are going to talk about. So this is our optical link based on a micro-ring modulator. And here we have some signal encoding and bit mapping, and then electrical driver is fed to micro-ring modulator integrated with the CW laser. Further, we use single mode fiber to transmit the signal, and it is received and processed on the receiver side. And this is something we would like to simulate. However, we want to pay specific attention to the modeling of micro-ring modulator. And to be a little more specific, we want to perform a circuit level simulation. We want to use something which is already implemented in VPIcomponentMaker photonic circuits. We want to model dopant-induced effective index and attenuation effects, as well as electrical properties of micro-ring modulator. And finally, we would like to perform micro-ring modulator characterization and prepare the device for the powerful transmission over single mode fiber. So how do we do that? The solution is already implemented in the product called VPIcomponentMaker photonic circuits. So it could be used for very different type of applications. Here you can see a few examples of them. And probably one of the typical example is this hybrid tunable 3.5 silicon laser with some active section here and passive silicon-based ring reflectors to form the cavity. And it is important that one can not only design and study design alternatives, but also do design optimization of such devices and investigate tolerances and perform sensitivity analysis. So there are models provided with the product, and some of them are fairly simple, as for example, for passive components, for waveguides or multi-mode interference devices. Quite common is to use scattering matrix approach with scattering matrices calculated, for example, based on analytical models, which are specific for each particular module. So then we can combine individual components in some compound devices, and their scattering matrices are calculated automatically. Surely there is provided framework for your own code implementing the models. And finally, scattering matrices could be either measured or calculated by device level simulators. However, the fact that the models in circuit level simulator are analytical or compact models doesn't mean that they are inaccurate. Some of them are actually pretty advanced, and here we can see the example of a transmission line model. And so this model allows for description of dynamics in the semiconductor devices, including non-linearities and carrier and photon dynamics and spatial hole burning effects in lasers and amplifiers. So one can also study bidirectional effects, for example, of the light backscattered into the cavity. And this implies some specific simulation approaches, and Jim will talk a little more about that. Okay, let's come back to the micro-ring modulator. So in general, micro-ring modulator consists of a ring-shaped waveguide which traps the light from the bus waveguide nearby. And this effect strongly depends on the light wavelength and the optical path of this modulator. So if we introduce some modulating section here, for example, based on reversed bias, PN junction, And so when we apply reverse bias to this PN junction, so if we bias in reverse direction, we change the effective index, and we change the optical path of this ring. And this allows us to tune the spectrum of this ring and perform modulation. And as Chris mentioned, this device has a lot of benefits. For example, it's very power efficient. It's still relatively high speed, and actually you can check this paper here, which we inspired our design. Further, if we introduce here a heater, we could tune the phase and tune our wavelengths over a pretty wide range. Finally, it has this strong inherent wavelength selectivity, and this is specifically attractive for CWDM applications. So how do we model that? We can surely use traditional methods based on the solution of the Maxwell equations, and we can also perform multi-physics simulation and account for current and heat distributions and so on. However, usually this kind of simulation takes a lot of time, and it's just not feasible for system level simulation. So instead, we use a circuit level simulation approach. And within this approach, it is proposed to segmentize the device as a whole structure into separate standard building blocks. And, the first advantage, it makes it much faster. Because we separate device level simulation, right, which is needed to characterize the individual components from the actual circuit level simulation, right? Further, we can control accuracy because individual building blocks can be modeled by different methods, and so we can easily balance between accuracy and speed requirements. However, still there should be ways to customize the models, and all these features make these kind of simulations feasible for system level simulations I mentioned at the very beginning. So this is VPI Design Suite, right? And here on the left, we have a library of components and, for example, laser sections or passive devices I've been showing before, as well as there are different optical and electrical sources available, as well as analysis and instrumentation tools. So further, in the application example tab, there are hundreds of the demonstration examples available with step-by-step instructions, and they're provided for each product. Okay, finally, I organized some demos for this webinar in a project here. And let me open the first one. And here we can see already a ready-to-use model of the modulator. Right, so we can have a look at the parameters it characterized. So still there are some geometrical parameters which could be adjusted, right? Other parameters could be, as for example, effective index and group index could be calculated with device level simulators, which we did with our VPI mod designer. Other parameters could be tuned in order to meet some experimental characteristics. So for example, we tuned attenuation to meet the desired extinction ratio value. And finally, we can switch the junction model, right, from physical or behavioral. And this is something we would like to have a little closer look at. Before I do that, let me just mention that VPI Design Suite supports hierarchical design approach. So our schematic is a top layer of simulation. However, it is possible to save some parts of the schematic for further simulations and use this kind of compound models equivalent to built-in models, as for example, analyzer or other models, right? So let me look inside of this modulator, get a little closer. Okay, so here's our implementation of the ring modulator based on our standard building blocks. So for example, this X coupler was taken from this library. And actually it is pretty simple ideal models, which is characterized by just coupling power ratio, which still could be controlled. in our simulation, right? But let's pay more attention to our PN junction segment. And this one is modeled with waveguide modulator, which is also can be taken here. So this is standard module, right? But we customize it a lot. So without going deep into the details of how this model operates, let me just mention that its effective index, group index, and attenuation could significantly depend on the applied voltage, right, applied to this port here. And this is implemented by a very important feature that the expressions describing these dependencies could be specified directly in the parameter editor, right? So-called parameter expressions, and they should be written in Python with $V variable standing for the value of applied voltage. Again, this is the voltage applied to this port here. And let me switch back for a minute to the upper level and have a look at this and this behavioral junction model. So for example, if we know this expression, we can specify it directly. So if we know directly how effective index depends on the applied voltage, we can specify this expression, and this is great. It gives us lots of flexibility. So our model is actually technology agnostic, right? So once we know that, we can specify this. The same we can do for attenuation. However, in our simulation task, we decided that we want to account for the physical properties of silicon in order to calculate the effective index and attenuation dependencies. And let's see how we can do that. So I would like to acknowledge these authors and their publications, which we used to base our junction model. And here we can see the equations which describe plasma effect in silicon. And again, I'm not going very deep into the details of these equations. I just want to mention that both effective index and attenuation change could be split into parts. So one is due to doping, this impurities doping of N and P type in our junction, right? So they already introduced some changes in the effective index. And another is due to change in size of this depletion region once we apply voltage, right? So it changes, and it also changes our effective index and performs modulation, therefore. So how these equations could be modeled in our simulation. And this could be achieved by the so-called initialization script. And let me open it here. So here's our initialization script. And this is a script, Python script, which allows for, it could contain some import statements. For example, we import here CPI library, which gives access to the very advanced methods for scientific calculations. But what is more important, it also allows us here to define our own functions and initialize our own variables. And everything defined here becomes directly available in the simulation and in the parameters of our modules. So for example, if we switch back to the effective index parameter, we see here this function is called, and we can actually find this function here in the init script. And in similar manner, we can implement these equations. So I switch to this function, and we can see that this function implements these equations. So this is a very advanced feature because it allows us very easily high level of customization, right? So we can call any code here. We can actually call and launch third-party software from here. So it calculates the parameters, and then these values passed to the simulation on the circuit level, and this all done interactively. So you do not need to move any files or values manually. Okay, So this is, I think, all about the model at this point. So let me switch back to the simulation. And this simulation shows an optical transmission spectrum of the ring modulator. And we want to see how it depends on the applied voltage. So here we have DC source, and we want to sweep its voltage. And for this, we use interactive simulation. So here we can define some variable controls. We can define the limits and step and assign it to the parameters in the simulation. Okay, so let me run the sweep. So again, what's going on? We sweep the value of the DC source and see how optical spectrum transmitted through the transfer function of our ring modulator changes, depending on the wavelength. Okay, and we can see that as soon as both effective index and attenuation change with applied voltage, our spectrum shifts both in the horizontal direction with wavelength and in vertical direction as well. And so we can use this characteristic further. If we remember, here we have this phase shifter, this thermal heater here, and we also can tune the phase shift and see how changing the phase shift in this passive tuning section changes our ring transfer function, right? And this is this could be used to tune modulator for the required operation wavelength. And for example, here we showed this phase shift approximately equal to 110 degrees to operate at the wavelength of 1290 nanometers. And now what we can do, we can study how the transmission at this particular wavelength depends on the voltage, on the applied voltage, and probably as well on the phase shift of our heater phase shifter. And for this, we have another schematic. So let me open the second schematic. And it's actually very, very similar to the previous one, with the only change that we have this CW laser here, input to the modulator, which is already tuned to operate at this 1290, wavelength. And actually, I already pre-run the simulation. It takes just a couple of minutes, but I'm gonna save that time. And yeah, we can see how the transmission at the particular wavelength depends on the applied reverse bias and the phase shift of the heater phase shifter. Okay, and this can be used to choose operation point, for example, and the voltage swing for our pump or any other required modulation format. And for multi-level simulation, it is always trade-off between the linearity of the transfer function and the extinction ratio we can achieve. So for our further simulations, we will choose these 2 volts, or better to say -2 volts, as soon as we are talking about reverse biasing, as a bias value for our modulator. So by now, we've been talking and studying purely static characteristics and the optical properties of the modulator. However, once we start applying modulation, parasitical electrical effects come into play. And so we come to the second requirement of our model, being able to simulate electrical properties of the modulator. And probably somebody already noticed this another model here. Let me look inside of that. And we can see that here we implement the equivalent circuit model of the carrier depletion ring modulator, following this reference here on the bottom. And so we combine both wire bonding equivalent circuit with the equivalent circuit of the intrinsic ring modulator. And one final thing I want to mention is that this capacitance we have here, capacitance of the PN junction, it depends on the applied voltage, and we can also simulate that. And let me switch directly to electro-optical modulation transfer function. So in this schematic, we use small signal analysis by driving our modulator with a low amplitude sine electrical signal here. And the modulation response of the electrical equivalent circuit could be either taken into account by this bottom part or switched off. And again, I pre-run this simulation, so let me save this a few minutes, literally. And yeah, here we can see the results. So we swapped over different frequencies, modulation frequencies this time, and calculated the amplitude response of the modulator. And we can study it both in case of like disregarding the equivalent electrical circuit, and also we can check how these electrical properties of the modulator affect the modulation response and modulation bandwidth. And such modulation characteristics can be used, for example, for the design of a transceiver equalizer. And so I gradually pass to the last demonstration. Okay, let me probably close our results and run this simulation where we actually apply PAM4 modulation to our ring modulator. And we can actually see that some white noise, amplitude noise was applied to the driving electrical signal. We actually drive it at 25 gigabaud symbol rate. Yeah, and we bias it at -2 volts. And yeah, let's see the response of the modulator. So here we can see the waveform and optical eye diagram. And again, you know, for PAM4 transmission, non-equidistant spacing between powers is a common problem, and we can surely play around with applying some non-equidistant levels on the driver side, but it's already the task for the system designer. And at this point, I pass my presentation to Jim. And yeah, thank you for your attention, and please do not forget to ask the questions in the Q&A box. And yeah, Jim, the floor is all yours.
What I wanted to talk about is taking the work that Eugene just displayed and talked about and promoting that up into a system model. So we'll talk about, first of all, what do I mean by a system model? But the big question is, why would you want to do that? Well, you have this modulator that has all of the, let's say, bias dependence and lots of other geometric parameters that need to be optimized for it in the design. So you have this complex system, this device that Eugene talked about, and now you want to put it into a system that has, let's say, even optical fiber in it. And the optical fiber is going to have linear distortions, linear impairments, but more complicated, it's going to have a lot of nonlinear characteristics to it as well. And so kind of taking your device, putting it into a real system, I mean, allows you to really look at how it's going to work with fiber or other components in the network, as well as any DSP that you may have added on top of that. There's another reason, and that is if you get someone who's doing a PIC design and they're given a set of requirements, and let's say they're doing a 90-degree hybrid or something like that, and so they're given by the system engineering group that they have to have the imbalance less than 2 degrees or something crazy. And so the PIC designer is kind of going crazy, like, how am I going to get any kind of yield with this phase error requirement that came out. Well, it turns out that there are DSP algorithms that can correct for things like phase imbalance in a 90-degree hybrid. And so now you just got to turn on the DSP guys and kind of do a trade-off on, okay, how much work do you want the DSP to do and how much work do you want the device designer to do in order to meet the spec. So there's lots of reasons why you would want to do system modeling. So what do you need to do system modeling? Well, you need optical sources. You need to model fiber propagation, both single mode and multi-mode. You need network components like filters, EDFAs, Raman amps, and lots of other things. It's nice to have a bunch of canned transmitters for all the various formats that are out there. Coding is becoming more and more important. You know, everything from forward error correction kind of coding to doing 24-dimensional modulation, and you know, there's lots of things, reasons to do this. Like probabilistic coding is another example. Signal analysis, you need to be able to look at things, so scope, spectral, so OSAs, RF spectrum analyzers, and then you want to do benchmarking, so you need to do things as basic as like symbol error rates. But there's lots of other things that you might need to be able to do. Also, you need to have DSP capability, and I'll demonstrate some of that as we go along. So let's look at a few of these ingredients. So you have the fiber models, and this is one of our fiber models. We call it the universal fiber model. It's bidirectional, linear impairments, kernel linearities, Raman, Bruin, polarization effects, as well as the polarization dependencies of all the nonlinearities, and it will do PMD simulation. So this, I often say, this is about as close as you're going to get to a piece of glass in a simulation tool. If you pump enough energy into it, it's a Raman amplifier of any order that you'd like. It just does this naturally. The universal fiber forward is essentially the same fiber, but you only have access to the forward. It kind of speeds things up and streamlines it a little bit. So it's not bidirectional, it still has all the nonlinearities, not Bruin, because that's really a bidirectional kind of thing, polarization effects in PMD. Then also multi-mode fibers. So the multi-mode fiber that we have is you use a mode solver or measured to get the characteristics of the fiber itself, and it uses that to characterize the fiber and calculate all the propagation. And so it uses a mode solver or a measured. It takes into account kernel linearities as well as mode coupling. Optical sources, there's lots and lots of optical sources. This is a few of them. Everything from a simple CW laser, which is the most common thing people slap in unless they're really interested in a lot of details. There's a rate equation laser that'll show you all the noise characteristics and accurate modeling of the sidebands and things like that. An analog laser, optical impulse. This is a nice thing. Instrumentation, if you want to look at frequency response of passive components. We have a multi-mode VCSEL model. It's actually pretty sophisticated. LED, a WDM comb, and then just an optical noise source, a Gaussian noise source. Network components, there's so many. I mean, there's all kinds of filters, muxes, combiners, optical filters, cross couplers, polarization controllers, as well as EDFAs, multi-mode EDFA, SOAs. And then very important if you're doing any kind of DSP or signal processing, we have a realistic DAC model that allows you to adjust the offsets and nonlinearities and things like that, both for the DAC and the ADC. So there's lots more components, network components that you need to really build a real system. So let's talk about simulation domains. So if I look at the fiber models and the filters, and actually many more of the elements that are used in system modeling, they're really best simulated in the frequency domain. So what does that mean? It means that each module must have a complete spectral information before they can calculate the output. And that requires a complete time window worth of data. So you have to go through the whole time window or the modeling time that you're doing for your simulation, and then pass that data to the next module in order for it to do an FFT or an inverse FFT or anything like that. It needs the complete data record. So we call this block mode. It operates by passing complete time window worth of data from module to module. Most system simulations are performed in block mode, and that implies periodic boundary conditions. And that's really best for when you're doing FFTs. That's really kind of a requirement when you're doing Fourier transforms. In contrast, simulations performed in sample mode, which is what Eugene was using for the devices, and this allows for bidirectionality and lots of things block mode does not, and that implies an aperiodic boundary condition. So now the job is, well, let's look at these two. So if you look at the device modeling, you inject a signal. This just changes it from a whole time window to it's going to send out individual samples. And these individual samples then circulate around the model. And I'm only showing one direction just because it would be too confusing with two directions. And these keep going round and round until you get some outputs. So you see some ringing here, and then you have the output with the ringing on top of there. But the important thing is that there's a whole train of data running through this whole section here, and because it's in the time domain. And you need to do time domain because these devices, these active devices, the counter-propagating fields will interact through things like the carrier densities and things like that. So block mode, the first thing that happens is, let's say the laser in the beginning of this very simple link starts and does a whole calculation for the whole time window. Then when that's done, it passes that time window worth of information to the next module. In this case happens to be fiber. And this laser module now is not used anymore. We're done with it. And so now you just, the universal fiber does its job, the detector does its job, and then you have, coming out of the detector, you have an electrical signal going into a filter, and then it goes to the visualizer or the analyzer that you can look at a scope or something like that, and you'll actually see this data plot here. So each block fires sequentially, and then you don't worry about it, and it passes the data after calculating the results for the entire time window. So the things are very different. You can see that you really can't do bidirectional modeling very easily with this at the same type of bidirectional modeling that you would do in devices that Eugene showed you. So now how can you perform simulations containing device and system elements? Because now they're really in different simulation domains. So you have, let's say you have a driver of a system. It's going to be in the system mode, let's say. So you're in block mode, frequency domain, periodic boundary conditions. That's going to drive the device, similar to what Eugene showed you. That's in the time domain, sample mode, aperiodic boundary conditions. And then you're going to go to the rest of the system. It could contain fiber and amplifiers and DSP and anything else you want. The problem is that you can't transfer data from between these domains. You're going from periodic boundary conditions to aperiodic boundary conditions, and that's a problem. So you need something in order to solve that problem. So we have a convenient module that's called the boundary condition converter, and so you're in the system here. So you're in periodic boundary conditions. You go through the boundary condition converter, change it to aperiodic boundary conditions. So now you're okay with the device modeling, and then you come out and go back to periodic boundary conditions and finish off the system. So in here you could have a driver, let's say the PAM driver. That's going to be driving the micro-ring modulator. And the device section we have that's done in the time domain and aperiodic boundary conditions. You have the device that Eugene was modeling. And then the rest of it's going to be fiber, detectors, amplifiers, some DSP, and then looking at the symbol error rate when we're done. So this is the complete system. So here you have the driver over here, the device, and then the rest of the system that's sitting there. So let's go to device simulation. So here's the model of that I just showed you. So here's driver, device, and all that. Let me start this up here. It takes less than a minute, but I'm very impatient. So anyway, so this guy is going to create the drive signal. It's going to have any kind of pre-distortion in it. If I look at the parameters, there's some numbers here that show you the levels of things, and this is going to really kind of pre-distort things so you can have evenly opened eyes for each of the three eyes that you have in the system. Then you go into this driver, which essentially just adds a bias to it. You go into the device. This is a module that allows us to run this more than one time before we output a block, and that gets rid of any initial transients and things like that. So I have this set to run twice, and then it sends that signal through the rest of the system. So you have fiber, detector, there's just an inverter, some filtering. This is like kind of a clock recovery, module scaling, DSP, and then into the symbol error rate estimator. So if we go look at this now, I have the fiber length set to 40 kilometers, and it's about 26 gigabaud is the rate. And so here's the drive signal at this point. You can see that it's pre-distorted. This eye is much more open than these guys. But then if you look at the received one that's at the detector, you can see that it's a little bit noisy because it's going over 40 kilometers of fiber, and it's tens of microwatts worth of power. So there's a lot of noise in here, and so this is that cleaned up a little bit through some filtering, and then you go through the DFE, and this is the output of the DFE, and you can see it tries to open up the windows. Since this is noise limited, it has problems, but it's doing pretty well at 40 kilometers. This shows the probability distribution functions for each of the symbols and the decision points. And here's the symbol error rate, which is about 5.5, 10 to the minus 7, which isn't too bad. So now if we want to go a little bit further and do a little bit more study, we could look at looking at the symbol error rate versus fiber length. And again, let me run this a little bit. So I added a couple modules to that previous model. This one in particular is just going to repeat the signal 11 times. I'll explain why 11 times. There's another module here. Another module here that's called a parameter controller. We used to call it the magic module. I like the magic module name better. But anyway, what happens is it takes whatever value you have here and applies it to a specified parameter in the next module, and this is the way I have it configured. And so here it's going to be adjusting the length given this ramp. So each time this thing fires, the ramp's going to go up. So it's going to start at 0 and increment by 5 kilometers, the fiber every time. And then way at the end, I added the same ramp that's here, and we're going to plot what's coming out at that point. And so this is the final result. So you have, again, the drive. This is the received signal, and this is essentially back to back. I'll show you what happens as we propagate. This is before the DFE. This is the output of the DFE, and here's the plot for a symbol error rate versus fiber length. And you can see we can get pretty far with this device at 26 gigabaud. The other thing I can do is I can look and see what happens to the eye as I add 5 kilometers each step, and you can see the eyes, getting noisier and noisier. There's not a whole lot of dispersion at this point, and so the DFE can't. It's fighting to fix that, but and then finally get up to 50 kilometers, and it's not very happy. It's pretty noisy, but it's almost okay. So I'll go back here, and if I look at, let me get this out of the way here. If I look at the other module, and I look at now, I want to look at 56 gigahertz, 56 gigabaud. Let's push it a little bit. And I like this one because there's a lot more dispersion. Same drive. This is 20 kilometers. After 20 kilometers, this is what the received signal looks like, and you can see it's a mess. Again, filtered a little bit, it's still a mess. But because it's dispersion, the DFE can actually do a lot more, and it can do a lot more to fix things. And so this is what you get at 56 gig at that point. Another thing, just to mention here, the reason why I did the sweep with this repeat and the ramps and everything else is because I don't want to have to recalculate this for every fiber length. I just calculate it once and then propagate that same signal each time over a different fiber length to see how it does. All right. So other things that you can do in system models, you can have a PAM source, and you have let's say FFE, and you want to measure TDECQ, for example. Eugene mentioned that these are hierarchical, and so I can look inside this FFE, and in here, in this guy, this is using co-simulation. Our tools will co-simulate with Python, any C++, any kind of exe file, DLL file, and so that helps a lot, and that's what this module does. These are all just conditioning the signals to go into the Python code that's sitting inside there. If I look at the other one that we had, by the way, and I go back to this guy, this is actually made of modules that are in the tool. And the reason why I show you this is that you can get down pretty low. I mean, there's logic gates, there's all kinds of things in the library here. So there's lots of things that you can do. So actually this DFE is actually implemented using LMS filters and things like that are in the device library. So back to, let's see, TDECQ. I didn't run it, so let me go to outputs here. It takes about a minute to run, something like that. It's not too long. And so this is the output here. So you have the received signal, then the signal after it goes to the FFE equalizer, and these are just the cumulative distribution functions, and looking at different probability distribution functions for each of the symbols, and then finally measuring TDECQ at some point here. I think that's this guy, 2.5. And so this module, this TDECQ model, is it's used in a demo. It may not be, because this standard changes all the time, it may not be completely up to date, but there are other things you can do that will give you more sophisticated TDECQ measurements, and I'll show you that in just a sec. Okay, so one of the other things that we have, and I mentioned DSP, and just really very quickly, the tool has built-in DSP library. In this example here, if I just look inside, you can see that there's these DSP modules. These are standard modules in here, and I can do things like frequency shift, the Kramer's quantity receiver, blind phase search, on and on and on. And I can also provide my own if I want. I can have my own module sitting there. So each one of these is now doing a different function. There's the MIMO equalizer, carrier frequency recovery, and then phase recovery. We also have a DSP library add-on, and it's a little bit more sophisticated. It's using state-of-the-art algorithms that are lab proven. These are all from HHI. And in here you have a pretty vast library of different things that you can use, different DSP. And this is particularly an issue when you're doing more coherent communications, not so much with PAM. Of course, you do have DFE and FFE. But anyway, all right. And then, so let me just close this out. Okay. The other thing that we do, and recently announced, was an interface. Well, we've always had an interface to the ADS system we have for many years. And that's, so you have a system model that's sitting there, and you have a module in the middle of it that would say, hey, go to the ADS system, calculate whatever you need to do, and come back. We just developed something that's a little bit more sophisticated. Well, it's a lot more sophisticated. And so you can have an optical system and have ADS providing the input, and then pass the output back to the ADS system without really having to interact with VPI a whole lot once you've built the modules. And so if I go to, I'm gonna get rid of all these things here. Back to my slides. So what this interface will do is it allows you to build this ADS model that's sitting down here in the corner here. So you have electrical amplifiers, filters, whatever things that are sitting here. And then you have the optical system, which is that system that I just showed you. And then you come out and you have more a part of the electrical system that ADS is modeling. And so when you do this, okay, again, this is this module that's sitting right here. And so you could look at, the impact of the micro-ring modulator, and you're opening up the system modeling now to more of the whole system, where you have the driver and all of its idiosyncrasies, and the receiver and all of its idiosyncrasies, all folded into system modeling. And so you can look at, details of the characteristics of the micro-ring modulator. And you can do this to, produce all kinds of characteristics using the actual driver models and things like that. And this can be called many, many times, so you can look at some more dynamic situations with ADS. One of the other things too is that ADS has a really nice interface, and they have for a TDECQ measurement that's pretty sophisticated, and I'm pretty sure they keep it up to date. So that's also another way to do TDECQ. Okay, well, thank you. I hope you get something out of this. Where you can take a device and the device model that you have, promote it into a system, and do some pretty sophisticated modeling and analysis and optimization using a full system. All right, thank you.
So if we don't get to them, you can see our email addresses here. If it's something technical that Jim or Eugene were talking about, please email them. If it's something more about a collaboration or licensing, please reach out to me at the bottom there. Well, thank you. Well, thank you, Jim and Eugene, for sharing that information with us today. If your question did not get answered, or you want to reach out, please email us. We'd be happy to communicate with you. And so thank you for your time, and I hope you have a good rest of the day, everybody.
Thank you, everybody.
Thank you. Thanks, Chris, Eugene, and Jim, and thank you guys all for attending again.